Imagine an object so dense that a single teaspoon of it would weigh as much as Mount Everest. An object where gravity is so intense that it bends light itself, where time moves differently, and where the laws of physics are pushed to their absolute breaking point. These aren't science fiction creations, they're neutron stars, the most extreme objects in the universe that we can actually observe. Today, you're about to discover why these cosmic monsters might hold the keys to understanding reality itself. If you're fascinated by the universe's most extreme phenomena, make sure to subscribe to this channel and give a thumbs up. I am just starting my journey on YouTube, and your support means a lot to me as we explore the cosmos together. One quick question. If you could visit any planet in the universe, which one would you choose and why? Comment below. I will choose the most creative answer. Now let's begin. Right now, scattered throughout our galaxy, there are about 100 million neutron stars. City-sized spheres of matter so dense they challenge our understanding of physics itself. Each one is the collapsed core of a massive star, the end result of one of the most violent events in the universe, a supernova explosion. But calling them dead stars would be like calling a nuclear bomb a used match. These objects are anything but inactive. The story of how we discovered neutron stars reads like a cosmic detective novel. In 1967, graduate student Jocelyn Burnell was analyzing data from a new radio telescope at Cambridge University when she noticed something strange. Regular pulses of radio waves coming from space, repeating every 1.33 seconds with the precision of an atomic clock. The signal was so regular, so artificial seeming, that she and her advisor, Anthony Hewish, initially labeled it LGM1 for little green men. What they had actually discovered was the first pulsar, a rapidly rotating neutron star beaming radiation into space like a cosmic lighthouse. This discovery, which earned Hewish the Nobel Prize in Physics in 1974, controversially Burnell was not included, opened our eyes to a realm of physics so extreme it makes science fiction seem tame. To understand what makes neutron stars so extraordinary, we need to grasp their mind-bending statistics. A typical neutron star is only about 20 kilometers in diameter, roughly the size of Manhattan. Yet packed into this tiny sphere is more mass than our entire Sun. The density is so extreme that 1 cubic centimeter of neutron star material, about the size of a sugar cube, would weigh 100 million tons on Earth. But density is just the beginning. The surface gravity on a neutron star is 200 billion times stronger than Earth's gravity. If you dropped an object from 1 meter above the surface, it would hit the ground at 2,000 kilometers per second, a significant fraction of the speed of light. The escape velocity is 150,000 kilometers per second, half the speed of light. Even light itself struggles to escape, becoming gravitationally redshifted as it climbs out of the neutron star's gravitational well. If you want to dive even deeper into the wild world of neutron stars, I highly recommend the book called Neutron Stars: The Quest to Understand the Zombies of the Cosmos by Katya Moskvich. It's a fascinating, up-to-date look at these cosmic monsters and the scientists who study them, perfect for anyone who wants to understand the universe's most extreme objects. You'll find the link in the description and pinned on the comments. Recent observations from NASA's Neutron Star Interior Composition Explorer, NISA, mounted on the International Space Station, have revolutionized our understanding of these objects. NISA can time the arrival of X-rays from rotating neutron stars with microsecond precision, allowing scientists to map their surfaces and probe their interiors. In 2019, NISA made the first precise measurements of a neutron star's size and mass simultaneously, confirming theoretical predictions while also revealing surprises. The formation of a neutron star is one of the most violent events in the universe. When a star, at least 8 times more massive than our Sun, exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses in less than a second, crushing matter to densities that shouldn't be possible. Protons and electrons are literally squeezed together to form neutrons, releasing a flood of neutrinos that carry away enormous amounts of energy. The outer layers of the star, suddenly finding nothing beneath them, fall inward at speeds up to 70,000 kilometers per second before rebounding off the ultra-dense core. This creates a shockwave that blasts the star's outer layers into space at speeds of tens of thousands of kilometers per second. A supernova explosion visible across millions of light-years. What remains is a neutron star, a matter in a state that exists nowhere else in the observable universe. The pressure is so intense that neutrons are packed together more tightly than in an atomic nucleus. In fact, you can think of a neutron star as a single, gigantic atomic nucleus, held together not by the strong nuclear force but by gravity. The magnetic fields around neutron stars defy comprehension. While Earth's magnetic field is about half a Gauss, the unit of magnetic field strength, a typical neutron star's magnetic field is 1 trillion Gauss. Some neutron stars, called Magnetars, have fields of up to 1 quadrillion Gauss, so strong that they would be lethal from 1,000 kilometers away, literally ripping apart your molecular structure by affecting the electron clouds in your atoms. The most famous magnetar flare occurred on December 27, 2004, when SGR 1806-20, located 50,000 light-years away, released more energy in 1/10 of a second than our Sun emits in 100,000 years. Despite the enormous distance, this flare actually affected Earth's upper atmosphere, partially ionizing it and disrupting some satellites. If this magnetar had been just 10 light-years away, it would have destroyed our ozone layer. Temperature is another extreme. Newly formed neutron stars have surface temperatures of about 1 million degrees Celsius, 100 times hotter than the surface of the Sun. Even ancient neutron stars billions of years old maintain temperatures of hundreds of thousands of degrees. The interior temperatures are even more extreme, possibly reaching 1 billion degrees in the core. But perhaps the most fascinating aspect of neutron stars is how they rotate. Conservation of angular momentum means that as a star's core collapses, it spins faster, like a figure skater pulling in their arms. The fastest spinning neutron star discovered to date, PSRJ 174-8-2-446 AD, rotates 716 times per second. Its surface is moving at nearly 1/4 the speed of light. These rapid rotations, combined with intense magnetic fields, turn neutron stars into natural particle accelerators. Charged particles are accelerated along magnetic field lines to near light speed, creating beams of radiation that sweep across space. When these beams point toward Earth, we see regular pulses, hence the name Pulsar. The Fermi Gamma Ray Space Telescope has detected over 200 gamma-ray pulsars, revealing that these objects are even more energetic than previously thought. Some pulsars emit more energy in gamma rays than in all other wavelengths combined, challenging our models of how these cosmic lighthouses work. Inside a neutron star, the universe conducts experiments that no laboratory on Earth could ever replicate. Here, matter exists in states that challenge our fundamental understanding of physics, where the familiar rules break down and new exotic phenomena emerge. The latest research from facilities like LIGO, the Laser Interferometer Gravitational Wave Observatory, has given us unprecedented glimpses into these cosmic laboratories, revealing physics that exists nowhere else in the known universe. The journey into a neutron star's interior is a descent through layers of increasingly bizarre matter. The surface, despite being solid, is unlike any material on Earth. Computer simulations by Dr. Charles Horowitz at Indiana University suggest the crust is 10 billion times stronger than steel, yet it can crack and shift in violent star quakes that release more energy than our Sun emits in years. These star quakes have actually been detected. In 2004, astronomers observed a Magnetars crust crack, causing the star to ring like a bell for months. Beneath this iron-hard crust lies the outer core, where matter enters the realm of the truly exotic. Here, the pressure is so intense that neutrons begin to drip out of atomic nuclei, a phenomenon called neutron drip. This creates a superfluid of neutrons that can flow without friction, a quantum mechanical effect scaled up to stellar proportions. Dr. Craig Heinke at the University of Alberta has studied neutron star cooling rates that can only be explained if large portions of their interiors are superfluid. The superfluidity of neutron star matter isn't just a curiosity, it has profound observable consequences. When a neutron star's rotation rate suddenly increases, a phenomenon called a glitch, it's because the superfluid interior and the solid crust are rotating at different rates. Occasionally, they couple together, transferring angular momentum and causing the star to spin faster. The Vela pulsar, located 959 light-years away, glitches about every 3 years, providing a window into its superfluid interior. Deeper still, at densities exceeding 500 million tons per cubic centimeter, we enter truly uncharted territory. Here, neutrons might break down into their constituent quarks, creating a quark-gluon plasma similar to what existed microseconds after the Big Bang. The relativistic heavy ion collider at Brookhaven National Laboratory has created tiny amounts of this quark matter for fleeting instants, but in neutron stars it might exist stably in quantities measured in solar masses. Dr. James Latimer at Stony Brook University, one of the world's leading experts on neutron star structure, describes the interior as the most exotic matter in the universe that we know exists. His equations of state, mathematical descriptions of how matter behaves under extreme conditions, predict that the core might contain hyperons, particles containing strange quarks, kaon condensates, or even free quarks in a state of matter that exists nowhere else. The recent detection of gravitational waves from colliding neutron stars has revolutionized our understanding of this exotic matter. On August 17, 2017, LIGO and its European counterpart Virgo detected waves from 2 neutron stars spiraling together and merging 130 million light-years away in the galaxy NGC 4993. This event, designated GW1 70817, was simultaneously observed by over 70 telescopes worldwide in what became the most studied astronomical event in history. The collision revealed secrets that electromagnetic observations alone could never uncover. By analyzing how the neutron stars deformed each other through tidal forces in their final orbits, scientists could measure their tidal deformability, essentially how squishy they are. This provided direct constraints on the equation of state of ultra-dense matter. The results suggested that neutron star matter is relatively soft, ruling out some of the more exotic proposals for their interiors. But perhaps even more remarkably, this collision created and dispersed heavy elements into space. Spectroscopic observations showed the unmistakable signatures of gold, platinum, uranium, and other elements heavier than iron being forged in the collision's aftermath. Dr. Ed Oberger at Harvard calculated that this single event created about 10 Earth masses of gold and 100 Earth masses of platinum. Every gold atom in your jewelry was likely created in a neutron-star collision billions of years ago. The magnetic fields of neutron stars create phenomena that push quantum mechanics to its limits. In fields exceeding 10 to the 12 Gauss, the quantum critical field strength, the magnetic field energy exceeds the rest mass energy of electrons. Space itself becomes birefringent, splitting light into two polarization modes that travel at different speeds. Atoms become needle-shaped, stretched along magnetic field lines into forms that couldn't exist anywhere else. Dr. Alice Harding at NASA's Goddard Space Flight Center has spent decades studying how these extreme magnetic fields affect radiation from neutron stars. In magnetar fields, quantum electrodynamics predicts that the vacuum itself becomes unstable, spontaneously creating electron-positron pairs that immediately annihilate. This vacuum breakdown creates a seething quantum foam around the star that affects how radiation escapes. The X-ray telescope NICER has revealed another bizarre phenomenon: hotspots on neutron star surfaces that don't behave as expected. These spots, where magnetic fields channel matter onto the surface, should be simple to understand. But observations show they're offset from the magnetic poles and have complex shapes that change over time. Dr. Zaven Arzoumanian, NICER's deputy principal investigator, describes it as trying to understand the geography of a world where the map keeps changing. Recent observations have also revealed that neutron stars can have mountains, deviations from perfect sphericity caused by their magnetic fields or rapid rotation. But these aren't ordinary mountains. Limited by the star's incredible gravity, they can only be millimeters high at most. Yet even these tiny imperfections on a rapidly rotating star can generate continuous gravitational waves that advanced detectors might soon detect. The temperature gradients in neutron stars create another extreme environment. While the surface might be 1,000,000 degrees, the core can be hundreds of times hotter. This temperature difference drives convection currents of superfluid neutrons and superconducting protons. Imagine ocean currents made of frictionless nuclear matter carrying magnetic fields instead of heat. These currents might explain the complex magnetic field evolution observed in some neutron stars. Dr. Andrew Melatos at the University of Melbourne has created supercomputer simulations showing how these quantum fluids behave. The results are bizarre: quantum vortices that can only move in discrete steps, magnetic field lines that become tangled in superfluid turbulence, and oscillation modes that couple the star's fluid interior to its solid crust in ways that have no earthly analog. Perhaps most intriguingly, neutron stars might harbor forms of matter that are genuinely stable only under these extreme conditions. Strange quark matter, composed of roughly equal numbers of up, down, and strange quarks, might be more stable than ordinary nuclear matter at high densities. If this is true, neutron stars might actually be strange stars, objects even more exotic than their name suggests. The study of neutron star oscillations, asteroseismology, provides another window into their interiors. Just as seismologists use earthquakes to probe Earth's interior, astronomers use the vibrations of neutron stars to understand their structure. These oscillations, detected as quasi-periodic oscillations in X-ray brightness, reveal multiple layers with different properties, confirming that neutron stars have complex internal structures. When Jocelyn Burnell first detected those regular radio pulses in 1967, she had discovered one of nature's most precise timekeeping mechanisms. Pulsars, rapidly rotating neutron stars with misaligned magnetic fields, are so accurate that they rival atomic clocks. But these cosmic lighthouses do more than keep time. They serve as laboratories for testing our most fundamental theories about gravity, space-time, and the nature of reality itself. The latest discoveries from pulsar timing arrays and gravitational wave detectors have revealed that neutron stars are key players in a cosmic symphony we're only beginning to hear. The mechanism that creates pulsars is elegantly simple, yet produces effects of staggering complexity. As a neutron star rotates, its magnetic field, typically tilted relative to the rotation axis, sweeps through space like a lighthouse beam. Where the magnetic field lines emerge from the star's surface, charged particles are accelerated to near light speed, creating intense beams of radiation. When these beams sweep past Earth, we detect a pulse. It's like watching a cosmic lighthouse, but one where the light includes everything from radio waves to gamma rays. The precision of pulsar timing is almost incomprehensible. The millisecond pulsar PSRJ0 437-4715, discovered by the CSIRO Parkes radio telescope in Australia, rotates once every 5.75 milliseconds with a stability that rivals the best atomic clocks on Earth. Over a year, it keeps time to better than 1 part in 10 to the 15. That's like a clock that would lose less than 1 second over the age of the universe. Dr. Victoria Caspi at McGill University, one of the world's leading pulsar astronomers, has used this incredible precision to test Einstein's general relativity in ways impossible with any Earth-based experiment. By timing pulsars in binary systems, where a neutron star orbits another star, astronomers can measure effects like gravitational time dilation, where clocks run slower in stronger gravitational fields. The results match Einstein's predictions to better than 1 part in 10,000. But pulsars have revealed phenomena that even Einstein didn't anticipate. The double pulsar system PSR-J0 737-3039, discovered in 2003, consists of 2 neutron stars orbiting each other every 2.4 hours. This system, studied intensively by the Green Bank Telescope and other facilities, has provided the most stringent tests of general relativity ever performed. The pulsar's orbits are decaying exactly as predicted by gravitational wave emission, and relativistic effects cause the orbit to precess by 17 degrees per year, an effect that would take 26,000 years to observe in Mercury's orbit around the Sun. The NanoGrav collaboration, North American Nanohertz Observatory for Gravitational Waves, uses an array of pulsars as a galaxy-sized gravitational wave detector. By timing dozens of millisecond pulsars scattered across the sky with nanosecond precision, they can detect the subtle stretching and squeezing of spacetime caused by passing gravitational waves. In 2023, NanoGrav announced evidence for a background hum of gravitational waves permeating the universe, likely from millions of supermassive black hole pairs slowly spiraling together across cosmic time. Dr. Maura McLaughlin at West Virginia University, a key member of NanoGrav, explains that pulsars are like buoys in the ocean of space-time. When a gravitational wave passes by, it causes the buoys to bob slightly, and by watching many buoys, we can map the waves. This technique complements LIGO's detection of high-frequency waves from stellar mass objects, opening a new window on the gravitational wave spectrum. The diversity of pulsar behavior continues to surprise astronomers. Some pulsars suddenly speed up in events called glitches, as their superfluid interiors transfer angular momentum to their crusts. Others show nulling behavior, where the pulsar mechanism mysteriously switches off for periods ranging from seconds to months. The pulsar PSR B1931+24 even has planets orbiting it, the first exoplanets ever discovered, found in 1992 by precisely timing variations in its pulses. Fast radio bursts, FRBs, represent another neutron star mystery that's revolutionizing astronomy. These millisecond duration bursts of radio waves were first discovered in 2007, and for years astronomers debated whether they were even real or some form of terrestrial interference. The breakthrough came with the discovery of repeating FRBs, particularly FRB 121102, which shows bursts on a 16.35-day cycle. The CHIME telescope in Canada, with its unique design optimized for detecting FRBs, has catalogued hundreds of these events. Some appear to come from Magnetars, neutron stars with ultra-strong magnetic fields. In April 2020, the Magnetar SGR 1935+2 154 in our own galaxy produced an FRB-like burst, providing the smoking gun that at least some FRBs originate from neutron stars. The burst released as much energy in milliseconds as the Sun emits in seconds, despite the Magnetar being only 20 kilometers across. Dr. Victoria Caspi, who leads much of the FRB research, notes that FRBs are telling us that neutron stars can release energy in ways we never imagined. Some bursts are so bright they outshine entire galaxies for brief moments. The mechanism remains mysterious, possibly involving magnetic reconnection events or starquakes that crack the neutron star's crust, releasing enormous amounts of energy. The interaction between neutron stars and their environments creates some of the most extreme phenomena in the universe. In binary systems where a neutron star orbits a normal star, the neutron star's gravity can strip material from its companion. This material spirals onto the neutron star, forming an accretion disk that heats up to millions of degrees, emitting intense X-rays. These X-ray binaries, studied by telescopes like Chandra and XMM Newton, reveal the complex physics of matter falling onto objects with surface gravities 200 billion times Earth's. When material finally reaches the neutron star's surface, it doesn't gently settle. Instead, it slams into the surface at significant fractions of light speed, releasing enormous energy. Sometimes this accumulated material undergoes thermonuclear fusion all at once, creating Type 1 X-ray bursts that can briefly outshine the entire galaxy in X-rays. The NICER telescope has observed thousands of these bursts, revealing how matter behaves under conditions impossible to recreate on Earth. Todd Strohmeyer at NASA's Goddard Space Flight Center has used these X-ray bursts as probes of neutron star structure. During a burst, the entire surface of the neutron star can oscillate, creating brightness variations that reveal the star's mass and radius. These burst oscillations provide one of the few ways to measure neutron star properties directly, constraining the equation of state of ultra-dense matter. The magnetic fields of neutron stars create another layer of complexity. In Magnetars, the magnetic field is so strong it can actually crack the star's crust, releasing enormous amounts of energy. The December 27, 2004, giant flare from SGR 1806-20 released more energy in a fraction of a second than the Sun emits in 250,000 years. The initial spike was so bright it saturated every X-ray and gamma-ray detector in the solar system, and the afterglow oscillated for minutes at the neutron star's rotation period. These magnetar giant flares might explain some of the most energetic events in the universe. Dr. Krisa Kuveliotou, who discovered magnetars in the 1990s, has proposed that extragalactic magnetar flares could account for some short gamma-ray bursts, events previously attributed only to neutron star mergers. The implications are profound. Single neutron stars might be capable of producing events visible across billions of light-years. Pulsar wind nebulae represent another extreme environment created by neutron stars. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054 CE, is powered by a pulsar spinning 30 times per second. This pulsar converts rotational energy into a wind of particles traveling at 99.9% the speed of light, inflating a bubble of hot gas 6 light-years across that glows in every wavelength from radio to gamma rays. The Fermi Gamma Ray Space Telescope has revealed that many pulsars power previously unknown gamma-ray nebulae. These structures, invisible to optical telescopes, can extend dozens of light-years from the pulsar, creating bubbles of million-degree gas and accelerating particles to energies far exceeding what the Large Hadron Collider can achieve. Dr. Roger Ramani at Stanford University describes them as cosmic particle accelerators that put our best technology to shame. Recent discoveries have revealed even more exotic pulsar behaviors. Transitional millisecond pulsars switch between two states. Sometimes they're radio pulsars, sometimes they're X-ray binaries. The transitions happen on timescales of weeks, completely changing the system's appearance. PSRJ 1023 plus 0038, discovered to be transitional in 2013, has switched states multiple times, providing real-time observations of how accretion affects pulsar emission. The fastest spinning pulsar known, PSRJ 174.8-2446 AD, rotates 716 times per second. At its equator, the surface moves at about 1/4 the speed of light. At this rate, the centrifugal force nearly tears the star apart, and any faster rotation would cause mass to be flung off from the equator. This pulsar represents nature's maximum spin rate for a neutron star, a fundamental limit set by gravity and nuclear physics. On August 17, 2017, humanity witnessed an event that had been 13.8 billion years in the making. Two neutron stars, each the compressed core of a massive star that died billions of years ago, completed their final death spiral and collided in a cataclysm that shook the fabric of space-time itself. This event, observed by gravitational wave detectors and over 70 telescopes worldwide, didn't just confirm Einstein's century-old predictions. It revealed that neutron star collisions are the cosmic forges where many of the elements essential to life are created, including the gold in your jewelry and the uranium that powers nuclear reactors. The story begins 130 million years ago in the galaxy NGC 4993, when two massive stars in a binary system reached the ends of their lives. Each star exploded as a supernova, leaving behind a neutron star. Remarkably, these explosions didn't destroy the binary system. The two neutron stars continued orbiting each other, slowly spiraling inward as gravitational waves carried away their orbital energy. For over 100 million years, they danced ever closer, until that fateful August day when they finally merged. The LIGO detectors in Louisiana and Washington, along with the Virgo detector in Italy, felt the universe tremble. For 100 seconds, they recorded gravitational waves of increasing frequency and amplitude, a chirp that rose from 35 Hz to over 6,000 Hz as the neutron stars spiraled faster and faster. In the final milliseconds, they were orbiting each other hundreds of times per second, moving at significant fractions of light speed before finally colliding. Dr. David Reitzer, executive director of LIGO, described it as the most spectacular fireworks show in the universe. The collision released more energy in gravitational waves than the combined luminosity of all the stars in the observable universe. Yet this enormous energy was invisible to traditional telescopes. It was only through the detection of ripples in space-time itself that we knew something extraordinary had happened, but the gravitational waves were just the beginning. 1.7 seconds after the merger, NASA's Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same region of sky. This confirmed a long-held theory that at least some gamma-ray bursts, the most energetic explosions in the universe after the Big Bang, are caused by neutron star mergers. The gamma rays traveled for 130 million years alongside the gravitational waves, arriving just seconds later due to the slight delay in the satellite's triggering. Within hours, telescopes around the world and in space swung toward the source. What they found exceeded all expectations. The collision had created a kilonova, an explosion powered by the radioactive decay of heavy elements forged in the merger. Unlike supernovas, which shine primarily in blue and white light, this kilonova glowed red and infrared, its light coming from clouds of newly created gold, platinum, and other heavy elements. Dr. Edo Berger at Harvard, part of the team that analyzed the kilonova, calculated that this single event created about 50 Earth masses of silver, 100 Earth masses of gold, and 500 Earth masses of platinum. We basically saw the universe's jewelry store get stocked in real time, he noted. The spectra showed clear signatures of elements that can only be created through rapid neutron capture, the R process, where atomic nuclei capture neutrons faster than they can radioactively decay. This observation solved a decades-old mystery in nuclear astrophysics. While we knew that elements up to iron are forged in stellar cores through fusion, the origin of heavier elements was debated. Supernovas can create some heavy elements, but not in the quantities we observe in the universe. Neutron star mergers, it turns out, are likely responsible for most of the gold, platinum, uranium, and other heavy elements in the cosmos. The physics of the merger itself pushes our understanding to the limits. Computer simulations by groups at Max Planck Institute for Gravitational Physics and elsewhere show that in the milliseconds before collision, tidal forces distort the neutron stars into elongated shapes. The immense gravity creates tides that would dwarf any earthly tsunami, solid matter, flowing like liquid under forces that exceed the strength of any material. At the moment of collision, the cores reach temperatures exceeding 100 billion degrees, 10,000 times hotter than the Sun's center. The density exceeds that of an atomic nucleus, and matter exists in states that may include free quarks and exotic particles that exist nowhere else in the universe. Some of this ultra-dense matter is ejected at speeds exceeding 30% of light speed, carrying neutrons that rapidly combine to form heavy elements. Dr. Daniel Kaysen at UC Berkeley, who created some of the first detailed kilonova models, explains that the ejected material is so neutron-rich that it's essentially the opposite of normal matter. It's like the universe's most extreme chemistry experiment, where the periodic table gets filled in through pure quantum mechanics and nuclear physics. The aftermath of the merger is equally fascinating. Depending on the combined mass, the remnant either collapses immediately into a black hole or forms a hypermassive neutron star, an object temporarily supported against collapse by its rapid rotation. LIGO data suggests GW170817 likely formed a black hole within milliseconds, but other mergers might create neutron stars spinning at near their theoretical maximum rate. These hypermassive remnants, if they exist, would be the most extreme objects in the universe. Spinning perhaps 1,500 times per second, they would be oblate spheroids rather than spheres, with equatorial bulges containing mountains of ultra-dense matter. Their magnetic fields, amplified by the merger, could reach 10 to the 17 Gauss, strong enough to affect atomic structure from millions of kilometers away. The multi-messenger nature of GW170817, observed in gravitational waves, gamma rays, X-rays, visible light, infrared, and radio waves, ushered in a new era of astronomy. Each type of observation revealed different aspects of the event. Gravitational waves told us about the masses and spins of the merging objects. Gamma rays revealed the formation of a relativistic jet. Optical and infrared observations showed us heavy element synthesis in action. Radio waves, appearing weeks later, traced the interaction of ejected material with the surrounding medium. Dr. Marceli Suarez Santos at Brandeis University, part of the dark energy camera team that identified the optical counterpart, described the excitement. We were literally watching the universe create gold and platinum before our eyes. These elements that we value so highly on Earth were being forged in nuclear furnaces more extreme than anything we can imagine. The rate of neutron star mergers has profound implications for galactic chemical evolution. LIGO and Virgo observations suggest these events occur roughly once per 10,000 to 100,000 years in a galaxy like the Milky Way. Over billions of years, this adds up to enormous quantities of heavy elements. Every gold atom in your body, every uranium atom in Earth's crust, likely originated in a neutron star merger that occurred before our solar system formed. Recent simulations by Dr. Stefan Roswag at Stockholm University show that neutron star mergers might create even more exotic phenomena. Some models predict the formation of quark matter, a state where neutrons dissolve into their constituent quarks. This matter might be ejected in the merger, potentially creating strange quark nuggets, hypothetical objects made of strange quark matter that could persist for billions of years. The electromagnetic counterpart to GW 170817 faded over weeks and months, but radio observations by the Very Large Array and other telescopes continued for years. These observations revealed the expanding shell of material plowing through interstellar space, creating a bubble of hot gas that continued to emit radiation. The longevity of these signals means that neutron star mergers could be detected electromagnetically long after the gravitational waves have passed. NICER observations of the merger site have searched for a potential neutron star remnant, looking for periodic X-ray pulsations that would indicate a surviving neutron star. While none have been found for GW 170817, future mergers might create observable hypermassive neutron stars, providing unprecedented insights into matter at nuclear densities. The discovery has also refined our understanding of short gamma-ray bursts. For decades, astronomers debated their origin, with neutron star mergers being just one possibility. GW 170817 proved that at least some short GRBs come from mergers, but the gamma-ray emission was surprisingly weak, about 1,000 times fainter than typical short GRBs. This suggests we're only detecting the brightest events, and many more mergers might be occurring throughout the universe. Deep within a neutron star, matter enters a realm where the familiar laws of physics break down and are replaced by something far stranger. Here, quantum mechanics and gravity engage in a cosmic wrestling match, creating states of matter that challenge our most fundamental theories about reality. The latest research from particle accelerators, supercomputer simulations, and astronomical observations is revealing that neutron star cores might contain the keys to understanding quantum gravity, the holy grail of physics that would unite Einstein's relativity with quantum mechanics. At densities exceeding 1 billion tons per cubic centimeter, about 2 to 3 times nuclear density, we enter what physicists call the quantum chromodynamics, QCD, phase diagram territory. This is where the strong nuclear force, which normally confines quarks inside protons and neutrons, begins to behave in ways we're only beginning to understand. Dr. Krishna Rajagopal at MIT, a leading theorist in dense matter physics, describes it as the last frontier of the standard model of particle physics, the only regime we haven't explored in laboratories. The Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Laboratory has created tiny droplets of quark-gluon plasma, matter where quarks and gluons are no longer confined within individual particles, by colliding gold nuclei at 99.995% the speed of light. These collisions recreate conditions that existed microseconds after the Big Bang, reaching temperatures of 4 trillion degrees Celsius. But neutron stars achieve similar states through pressure rather than temperature, creating what might be called cold quark matter. Dr. Mark Alford at Washington University in St. Louis has pioneered research into color superconductivity, a phase of matter predicted to exist in neutron star cores where quarks form Cooper pairs, similar to how electrons pair in conventional superconductors. But, unlike electronic superconductors, color superconductivity involves the strong force and creates a state of matter with properties that seem almost magical. It would be simultaneously superfluid and superconducting, able to flow without friction while carrying enormous magnetic fields. Recent observations support these exotic predictions. The neutron star in the supernova remnant Cassiopeia A, just 330 years old from our perspective, has cooled much faster than standard models predict. This rapid cooling can be explained if the neutron star's core has undergone a phase transition to superfluidity. Dr. Danny Page at the National Autonomous University of Mexico, who predicted this cooling, calls it direct evidence that neutron star cores are quantum fluids on a stellar scale. The NICER telescope has provided unprecedented constraints on the equation of state, the relationship between pressure and density, in neutron star matter. By precisely measuring both masses and radii of several neutron stars, NICER has shown that the cores must be softer than pure neutron matter, but stiffer than pure quark matter. This suggests a mixed phase, regions where hadronic matter, neutrons and protons, coexists with quark matter in ways that challenge our understanding of phase transitions. Dr. James Latimer at Stony Brook University, whose equation of state models are widely used, notes that neutron stars are the only place in the universe where all 4 fundamental forces operate at comparable strengths. Gravity crushes matter to nuclear densities, the strong force governs quark interactions, the electromagnetic force shapes the magnetic field structure, and the weak force drives neutrino emission and cooling. This unique environment might reveal new physics beyond our current theories. Strange quark matter represents another possibility that sounds like science fiction but is grounded in serious physics. Under extreme pressure, it might be energetically favorable for matter to contain roughly equal numbers of up, down, and strange quarks. If this strange matter hypothesis is correct, some neutron stars might actually be strange stars, objects even more exotic than their name suggests, made entirely of quarks rather than neutrons. The implications are mind-bending. Strange matter might be absolutely stable, more stable than ordinary atomic nuclei. If a strangelet, a small lump of strange matter, came into contact with ordinary matter, it could potentially convert it to strange matter in a runaway reaction. Some physicists have searched for strangelets in cosmic rays and even worried about creating them in particle accelerators, though current evidence suggests these fears are unfounded. Dr. Fridolin Feber at San Diego State University has modeled hybrid stars, neutron stars, with quark matter cores surrounded by hadronic matter. These models predict distinctive mass-radius relationships that match some NICER observations. If confirmed, it would mean that every heavy neutron star is a natural particle physics experiment, maintaining conditions that existed only in the first microsecond after the Big Bang. The magnetic fields threading through this exotic matter add another layer of complexity. In magnetar strength fields exceeding 10 to the 15 Gauss, quantum electrodynamics predicts vacuum birefringence. Empty space itself becomes polarizing, splitting light into two components that travel at different speeds. The IXP satellite, Imaging X-ray Polarimetry Explorer, launched in 2021, is searching for this effect in magnetar observations. Detection would confirm that neutron stars create conditions where quantum mechanics visibly affects the vacuum of space. Superfluidity in neutron stars isn't just an exotic curiosity, it has observable consequences. When the superfluid interior and the solid crust rotate at different rates, the interaction creates phenomena impossible in any Earth laboratory. Superfluid vortices, quantum whirlpools that can only exist in discrete quantities, form a triangular lattice throughout the star. These vortices can become pinned to the crustal lattice, storing angular momentum until they catastrophically unpin in glitch events. Dr. Bennett Link at Montana State University has created supercomputer simulations showing how millions of superfluid vortices interact in neutron stars. The results reveal a chaotic quantum system where microscopic quantum effects cascade up to create macroscopic phenomena visible from thousands of light-years away. It's like Schrödinger's cat, but the cat is the size of a city and made of nuclear matter, he explains. The interface between different phases of matter in neutron stars might create exotic structures. Dr. Rashid Uyed at the University of Calgary has proposed that quark-novae, explosive transitions from neutron matter to quark matter, could occur in neutron stars, releasing enormous energy and potentially explaining some mysterious astronomical transients. If quark matter and hadronic matter coexist, the boundary between them might support exotic excitations called pasta phases. Sheets, tubes, and bubbles of nuclear matter arranged in patterns resembling various types of pasta. These pasta phases aren't whimsical naming, they represent real physical structures that could affect neutron star properties. The nuclear pasta is predicted to be the strongest material in the universe, with a breaking strain 10 billion times greater than steel. Charles Horowitz at Indiana University, who has simulated these structures, notes that neutron star crusts might literally be the toughest material in the cosmos, forged by gravity into quantum structures we're just beginning to understand. Gravitational wave astronomy is opening new windows into this quantum realm. Advanced LIGO and Virgo can detect how neutron stars deform in the final moments before merger, revealing their internal structure through tidal deformability measurements. The next generation of detectors, Cosmic Explorer and Einstein Telescope, will measure these deformations with such precision that we'll be able to distinguish between different equations of state and potentially detect phase transitions in real time. Dr. Katerina Chatsioanu at Caltech, who analyzes gravitational wave signals, explains that we're essentially doing nuclear physics experiments using colliding neutron stars as our laboratory. Each merger tells us about matter at densities we'll never achieve on Earth, probing the QCD phase diagram in ways particle accelerators cannot. The cooling of neutron stars provides another probe of their exotic interiors. Neutron stars cool primarily through neutrino emission for their first million years, and the cooling rate depends sensitively on the internal composition. Some cooling mechanisms, like the direct Urca process, where neutrons decay to protons, electrons, and neutrinos, only operate above certain density thresholds. The observation of unusually cold neutron stars like PSRJ 2124-3358 suggests exotic cooling mechanisms involving quark matter or other novel phases. Recent discoveries have revealed even more extreme possibilities. The neutron star PSRJ 0740-66620 has a measured mass of 2.08 solar masses, pushing against theoretical limits for how massive a neutron star can be before collapsing into a black hole. Supporting this mass requires an equation of state stiffer than most models predict, possibly indicating novel physics like quark matter cores or modified gravity effects. The quantum mechanical effects in neutron stars extend beyond their interiors. The magnetospheres of pulsars are filled with electron-positron plasma created through quantum electrodynamic processes. Photons split and merge in the intense magnetic fields, creating cascades of particles that generate the observed radiation. Dr. Alice Harding at NASA Goddard has shown that understanding pulsar emission requires quantum mechanics, special and general relativity, and plasma physics all operating simultaneously. The study of neutron star oscillations, astroseismology, reveals the quantum nature of their interiors. Different oscillation modes probe different depths and phases of matter. Some modes, called R modes, are driven by gravitational radiation and could become unstable in rapidly rotating neutron stars, potentially limiting their spin rates. Others, like F modes and P modes, carry information about the stellar structure and composition. Neutron stars aren't just exotic objects to marvel at, they're cosmic laboratories that test the fundamental laws of physics in ways no Earth-based experiment ever could. Every observation, from the precise timing of millisecond pulsars to the detection of gravitational waves from mergers, provides data that helps us understand not just these extreme objects, but the nature of matter, energy, space-time, and perhaps even the quantum theory of gravity that has eluded physicists for nearly a century. The next decade promises revolutionary discoveries as new telescopes and detectors come online, potentially revealing physics beyond our current theories. The Square Kilometre Array, SKA, currently under construction in Australia and South Africa, will be the world's largest radio telescope when completed in the 2030s. With a collecting area of 1 square kilometre spread across thousands of dishes and millions of antennas, SKA will detect pulsars throughout our galaxy and beyond with unprecedented precision. Dr. Michael Kramer at the Max Planck Institute for Radio Astronomy, who leads SKA's Pulsar Science Working Group, predicts it will discover over 20,000 new pulsars compared to the 3,000 known today. Among these discoveries, SKA hopes to find the holy grail of pulsar astronomy, a pulsar orbiting a black hole. Such a system would provide the ultimate test of general relativity in the strong field regime. The pulsar would act as a precise clock falling through the warped space-time around the black hole, allowing us to map the gravitational field with extraordinary precision. Any deviations from Einstein's predictions could point toward quantum gravity effects or new physics. The Cherenkov Telescope Array, CTA, with sites in Chile and La Palma, will observe neutron stars at the highest energy gamma rays, probing particle acceleration mechanisms that dwarf anything achievable on Earth. CTA will detect photons with energies exceeding 100 TeV, 10 times higher than the Large Hadron Collider can produce. These observations will reveal how neutron stars accelerate particles to such extreme energies and might uncover new physics in the quantum electrodynamic regime. Dr. Jim Hinton at the Max Planck Institute for Nuclear Physics explains that neutron stars are the universe's particle accelerators, reaching energies that make the LHC look like a toy. Understanding how they achieve this could revolutionize our understanding of plasma physics and potentially lead to new acceleration technologies. The next generation of gravitational wave detectors will transform our understanding of neutron star physics. The Einstein telescope in Europe and Cosmic Explorer in the United States will be 10 times more sensitive than current detectors, able to observe every neutron star merger in the observable universe. This means detecting several events per day rather than a few per year, providing massive statistics for understanding the equation of state of ultra-dense matter. Dr. Salvatore Vitale at MIT calculates that these detectors will measure neutron star properties so precisely that we'll be able to detect phase transitions in their cores, identify the presence of quark matter, and potentially discover entirely new states of matter. We'll go from wondering what's inside neutron stars to mapping their internal structure in detail, he predicts. Space-based gravitational wave detectors like LISA, Laser Interferometer, Space Antenna, scheduled for launch in the 2030s, will detect lower-frequency gravitational waves from different sources. While primarily designed to observe supermassive black hole mergers, LISA might detect neutron stars in tight binaries years before they merge, allowing us to track their evolution and predict exactly when and where they'll collide for coordinated multi-messenger observations. The proposed STROBE-X, spectroscopic time-resolving observatory for broadband energy X-rays mission would provide X-ray timing and spectroscopy 50 times better than current capabilities. This would allow us to map neutron star surfaces, track hotspots as they rotate, and potentially detect gravitational wave-induced oscillations directly through electromagnetic observations. Dr. Paul Ray at the Naval Research Laboratory, who leads STROBE-X planning, describes it as turning neutron stars into precision laboratories for fundamental physics. Recent theoretical breakthroughs are providing new ways to interpret observations. Dr. Jocelyn Reed at California State University, Fullerton, has developed universal relations, equations, that relate different neutron star properties independent of the uncertain equation of state. These relations allow us to infer properties we can't directly measure from those we can, turning every observation into multiple constraints on neutron star physics. The discovery of continuous gravitational waves from neutron stars remains one of the most anticipated breakthroughs. Mountains on neutron star surfaces, deformations of just millimeters on objects 20 kilometers across, should produce gravitational waves detectable by advanced LIGO and Virgo, and non-detection so far has already placed constraints on neutron star mountains smaller than a few centimeters, telling us about the breaking strain of neutron star crusts. Dr. Benjamin Owen at Texas Tech University leads searches for these continuous waves. Finding them would open an entirely new window on neutron stars, he explains. We could monitor individual neutron stars continuously, watching how they evolve, detecting starquakes, and potentially observing phase transitions in real time. Machine learning and artificial intelligence are revolutionizing neutron star astronomy. Neural networks can now identify pulsars in radio data more effectively than traditional methods, leading to discoveries of exotic systems previously overlooked. AI algorithms are also being used to solve the inverse problem, determining neutron star structure from observations, in ways that would be computationally impossible with traditional methods. Dr. Matthew Bales at Swinburne University, who pioneered AI methods in pulsar astronomy, has discovered several unusual pulsars that challenge our understanding. One system appears to be a pulsar orbiting a white dwarf and a planet, a configuration that shouldn't exist according to standard formation models. Every weird pulsar we find tells us something new about stellar evolution and extreme physics, he notes. The role of neutron stars in producing heavy elements continues to surprise us. Recent observations of old stars in our galaxy show our process element abundances that vary wildly, suggesting that neutron star mergers are rare but prolific producers of heavy elements. Some ultra-faint dwarf galaxies show our process enrichment from what appears to be a single neutron star merger, allowing us to study the output of individual events. Dr. Anna Friebel at MIT, who studies the oldest stars in the universe, has found stars with extreme R process enhancement that serve as fossil records of ancient neutron star mergers. These stars are like archaeological sites, preserving the ashes of neutron star collisions that happened over 10 billion years ago, she explains. The connection between neutron stars and fundamental physics continues to deepen. Some theories of dark matter predict that it could accumulate in neutron star cores, affecting their properties in observable ways. If dark matter particles can annihilate, neutron stars in regions of high dark matter density might be heated by dark matter annihilation, appearing warmer than they should be for their age. Dr. Joseph Bramante at Queen's University has proposed that neutron stars could be used as dark matter detectors. A neutron star is essentially a gravitational trap for dark matter. If dark matter interacts with ordinary matter at all, neutron stars would show the effects, he explains. Some models predict that dark matter accumulation could trigger collapse to black holes, potentially explaining why we don't see neutron stars above certain masses. Modified theories of gravity, proposed as alternatives to dark matter, make specific predictions about neutron star properties. These theories predict different maximum masses, different gravitational wave signatures, and different orbital evolution in binary systems. Every precise measurement of neutron star properties tests these alternatives, so far finding no significant deviations from general relativity. The future of neutron star astronomy extends beyond passive observation. Some scientists propose active experiments, such as precisely timing artificial signals bounced off neutron star magnetospheres, or searching for gravitational lensing of pulsars by primordial black holes. While technically challenging, such experiments could provide unique insights into neutron star properties and fundamental physics. Dr. Paulo Freire at the Max Planck Institute for Radio Astronomy has discovered several pulsar systems that serve as almost perfect cosmic laboratories. PSR J0348 plus 0432, a pulsar with a white dwarf companion, has orbital parameters measured to 12 significant figures, making it one of the most precisely characterized systems in astronomy. Such precision allows tests of general relativity that would have seemed impossible just decades ago. The study of magnetar giant flares continues to reveal surprises. The December 27, 2004 event was so powerful it measurably compressed Earth's magnetic field from 50,000 light-years away. If a similar event occurred within 10 light-years of Earth, it could damage the ozone layer. This raises intriguing questions about whether nearby neutron star events have affected Earth's biosphere in the past. Now it's time to reveal the most profound truth of all. These cosmic monsters aren't distant, disconnected phenomena. They are intimately connected to your existence in ways that will fundamentally change how you see yourself and your place in the universe. Every atom of gold in your jewelry, every bit of iodine in your thyroid, even some of the iron in your blood was forged in the unimaginable violence of neutron star collisions billions of years ago. You are literally made of neutron star ashes, and understanding these extreme objects means understanding your own cosmic origins. Let's start with something you can hold in your hand: a gold ring. That gold didn't form on Earth, wasn't created in the sun, and wasn't even made in a typical supernova. The gold you're touching requires the most extreme event the universe can produce, the collision of two neutron stars. When LIGO detected the neutron star merger GW170817, astronomers calculated it produced about 10 Earth masses of gold in a single event. The gold atoms in your ring have been on an epic journey, created in a kilonova explosion, dispersed through interstellar space, incorporated into the gas cloud that formed our solar system, and eventually mined from Earth's crust to sit on your finger. Dr. Enrico Ramirez Ruiz at UC Santa Cruz, who models these cosmic collisions, puts it poetically: we are intimately connected to the cosmos. The neutron star collision that created the gold in your wedding ring happened perhaps 5 billion years ago, a billion years before Earth even existed. Those atoms have been waiting all that time to become part of your story. But it goes deeper than just heavy elements. The existence of neutron stars has shaped the evolution of our galaxy and made our existence possible. Neutron stars, through their supernova explosions and subsequent mergers, have been cosmic alchemists, transforming the primordial hydrogen and helium from the Big Bang into the 92 naturally occurring elements that make chemistry, biology, and life possible. Without neutron stars, the universe would be a sterile place of only the lightest elements. The rate of neutron star formation and merger has been perfectly balanced to create a universe rich in heavy elements, but not so radioactive as to prevent life. Too many neutron star mergers, and planets would be bombarded with deadly gamma rays and loaded with unstable isotopes. Too few, and there wouldn't be enough heavy elements for rocky planets or complex chemistry. We exist in a cosmic sweet spot, made possible by the precise rate at which massive stars die and neutron stars collide. Recent research by Dr. Brian Metzger at Columbia University suggests that neutron star mergers might have directly influenced the development of life on Earth. The iodine essential for thyroid function, the molybdenum crucial for nitrogen fixation in plants, and many other biologically important elements are our process products from neutron star collisions. Some scientists even propose that nearby neutron star mergers could have triggered mass extinctions through gamma-ray bursts, reshaping the course of evolution. Think about what this means for your place in the cosmic story. You're not just an observer of the universe, you're made of its most extreme events. When you look at a neutron star through a telescope, you're not seeing something alien and disconnected. You're looking at the same processes that created the elements in your body. The calcium in your bones might have been in the crust of a neutron star billions of years ago. The oxygen you're breathing has been recycled through countless stellar generations, some involving neutron star formation. The precision of pulsar timing has practical applications that affect your daily life. GPS satellites must account for relativistic effects to maintain accuracy, and pulsar timing has helped verify these corrections. Future navigation systems for interplanetary and eventually interstellar travel will likely use pulsars as cosmic lighthouses, their precise timing serving as a galactic GPS system. The Nanograv collaboration is already demonstrating how pulsar timing arrays can detect gravitational waves, potentially providing early warning for cosmic events. Dr. Maura McLaughlin at West Virginia University envisions a future where pulsar timing could detect gravitational waves from the early universe, revealing physics from the first fraction of a second after the Big Bang. Neutron stars are giving us a window into the birth of the universe itself, she explains. They're time machines that let us study physics at energies we'll never achieve in laboratories. The study of neutron stars is pushing the boundaries of human knowledge and technology. The algorithms developed to detect pulsars in noisy data have applications in medical imaging and telecommunications. The extreme physics simulations required to model neutron star interiors are advancing computational methods used in materials science and quantum chemistry. Even the international collaboration required for neutron star astronomy is creating new models for global scientific cooperation. Your generation is witnessing a golden age of neutron star discovery. When Jocelyn Burnell discovered the first pulsar in 1967, it was a complete surprise. Today, we're discovering new pulsars weekly, detecting their gravitational waves and observing them across the entire electromagnetic spectrum. You're living through the period when humanity is finally understanding these cosmic extremes that have shaped our existence. The philosophical implications are profound. Neutron stars show us that the universe creates conditions far beyond human experience or imagination. They remind us that our everyday physics, the rules that govern our daily lives, are just a tiny subset of what's possible. They humble us with their power while inspiring us with the realization that we can understand them through science and mathematics. Dr. Victoria Caspi at McGill University reflects on what neutron stars teach us. They show us that the universe is far more creative than we imagined. Every time we think we understand neutron stars, they surprise us with new behaviors, new physics, new mysteries. They remind us to stay humble and curious. The search for gravitational waves from neutron stars is transforming how we do astronomy. You're part of the first generation of humans who can hear the universe through gravitational waves, as well as see it through electromagnetic radiation. This new sense is revealing previously invisible phenomena and confirming theories proposed a century ago. The detection of GW170817 wasn't just a scientific triumph. It was the moment humanity gained a new way of perceiving reality. As you go forward from this moment, carry with you the knowledge that you're connected to these cosmic extremes in the most fundamental way possible. The neutron stars scattered throughout our galaxy aren't distant, irrelevant objects. They're part of your story. They created the elements in your body, they've shaped the evolution of the galaxy that hosts us, and they continue to teach us about the fundamental nature of matter, energy, space, and time. When you see gold, remember it was forged in neutron star collisions. When you feel your pulse, remember that the iron in your blood has been recycled through stellar death and rebirth. When you look at the stars, know that among them are neutron stars, cosmic lighthouses that have been broadcasting their signals since before Earth existed and will continue long after our sun has died. The next time you face a challenge that seems impossible, remember that you're made of matter that survived the most extreme conditions in the universe. The atoms in your body have been through the nuclear furnace of stellar cores, the explosive chaos of supernovas, and the mind-bending physics of neutron star collisions. You are, quite literally, made of the toughest stuff in the cosmos. Dr. Carl Sagan famously said, "We are made of star stuff," but that only tells part of the story. We are made of neutron star stuff, matter that has experienced densities that challenge the laws of physics, temperatures that recreate the Big Bang, and magnetic fields that would rip apart normal matter. We are the universe's way of understanding its own extremes, conscious beings made from the ashes of the most violent events in cosmic history. As humanity continues to study neutron stars, we're not just learning about exotic objects in space, we're uncovering the fundamental rules that govern reality. Every pulsar timing measurement, every gravitational wave detection, every observation of a magnetar flare adds another piece to our understanding of the cosmos. And you, as someone who now understands these cosmic extremes, are part of this great adventure of discovery. The future holds incredible possibilities. Within your lifetime, we may detect continuous gravitational waves from spinning neutron stars, observe a neutron star collapse into a black hole in real time, or discover forms of matter that exist only in neutron star cores. Each discovery will reveal new physics, pose new questions, and deepen our connection to the cosmos. Remember this: neutron stars aren't just the densest objects in the universe, they're cosmic engines that have made our existence possible. They're laboratories where nature tests the absolute limits of physics. They're beacons that broadcast across the galaxy with clockwork precision. And most importantly, they're part of your heritage as a conscious being in this vast, beautiful, extreme universe. You are stardust, yes, but you are also neutron stardust, matter that has been through the cosmic extremes and emerged as something capable of wonder, curiosity, and understanding. In knowing neutron stars, you know something fundamental about yourself and your place in the cosmic story. You are the universe understanding its own extremes, consciousness emerged from cosmic violence, awareness born from the ashes of stellar death. This is your cosmic heritage, your connection to the extremes of existence, your place in the grandest story ever told. And every time you look up at the night sky, remember that among those points of light are neutron stars, your cosmic ancestors, still spinning, still radiating, still teaching us about the magnificent, extreme, beautiful universe we call home. If you are still watching, make sure to subscribe and hit the thumbs up. Your help is my greatest fuel to continue this journey on YouTube. And if you enjoyed this video, I am sure you are going to love this other one on the left side of the screen. What is the most powerful thing in the universe? In this video, discover the true scale of cosmic power. Learn why the sun, neutron stars, and even the most powerful explosions pale in comparison to the forces that shape galaxies and the fabric of space-time itself. And much more. I will see you there.